You can have the exact right equations and a flawless solver, and still get a completely wrong answer. Not because the physics is off, but because of the mesh underneath it. The mesh is the least glamorous part of CFD, and it's where a huge number of simulations quietly go wrong. A mesh is just the domain, chopped into cells. You build 1-2 broad ways. A structured mesh is a clean grid of quadrilaterals or hexahedra, lined up in neat rows, efficient and accurate, but it struggles to wrap around complicated shapes. An unstructured mesh fills the space with triangles or general polyhedra, bending around any geometry you like, at the cost of some efficiency. And remember, every cell is one of those control volumes from the finite volume method, the little box where the solver balances its fluxes. But not all cells are created equal. A cell can be the right idea and still be a bad cell. 3 things wreck cell quality: skewness, when a cell is sheared and distorted far from its ideal shape; aspect ratio, when a cell is stretched long and thin; and non-orthogonality, when the face between 2 cells isn't square to the line joining their centers. Each of these poisons the flux calculation, because the interpolation that estimates the value at a face assumes the cells around it are reasonably shaped. Feed the solver skewed, stretched, twisted cells, and the answer smears, oscillates, or the run simply blows up. Garbage cells, garbage result, no matter how good the physics. There's one place where meshing is hardest of all, right at a solid wall. At any wall, the fluid sticks. The velocity drops to exactly 0 at the surface, the no-slit condition, then climbs back to the free stream speed over a tiny distance. That thin region is the boundary layer, and inside it the velocity gradient is enormous. Almost everything you care about, drag, heat transfer, wall shear, is decided inside that sliver. If your mesh can't see the boundary layer, your simulation is blind to the very thing you're trying to predict. To capture that steep profile, you need cells packed in tight against the wall. The single most important knob is the height of the first cell, the one touching the surface. Make it too tall and it jumps clean over the boundary layer, smearing the gradient into nonsense. Pack them fine and you capture it. So, how tall is too tall? The answer can't be in millimeters, because the right size depends on the flow, the speed, the fluid, the local conditions. You need a dimensionless ruler. That ruler is called y+. It's the distance from the wall measured not in meters but in viscous units, scaled by the friction velocity and the kinematic viscosity. A y+ of 1 means your first cell sits right down in the thinnest, most viscous part of the boundary layer. A y+ of 100 means it sits much further out. It's the universal way to state how fine your near-wall mesh really is, whatever the case. And there are 2 legitimate answers. Picture the near-wall region in y+ units, a thin, viscous sublayer right at the wall, a buffer layer above it, then a region where the velocity follows a known logarithmic law. You can resolve the boundary layer, push the first cell down to a y+ near 1, and mesh all the way through the steep part. Or you can model it. Place the first cell out in the logarithmic region, around a y+ of 30 to a few hundred, and let a wall function bridge the gap. Both work. What you must not do is land in the buffer layer in between, where neither one holds. That's the no man's land that quietly ruins results. So the mesh isn't bookkeeping. It's where accuracy is won or lost. Keep your cells well shaped and treat the wall with respect. Decide up front whether you're resolving the boundary layer or modeling it, and size your first cell to the y+ that choice demands. Get the wall right, and the rest of the simulation has a chance. Get it wrong, and nothing downstream can save you. That's all for this video.